To find our way around on the real number line, we're going to need a measuring stick. That stick comes in the form of the absolute value operation, which measures the distance between any two real numbers. We're going to review the key properties, called the norm axioms, that give the absolute value the power to measure distance. And then we'll see how the triangle inequalities give us the ability to do probably the most important thing in analysis, which is to estimate distances between points from both above and from below. The absolute value measures the distance between two real numbers x and y as the absolute value of the difference x minus y. This gives a sensible notion of distance, because the absolute value satisfies the properties of a norm on a vector space. It's always non-negative. It's zero only when its argument is zero. Scalar multiplication can be pulled out. Notice it gets pulled out with an absolute value. But best of all, it satisfies the triangle inequalities. These tell us that the norm of a sum can be no larger than the sum of the norms, and conversely, that the norm of a difference can be no smaller than the absolute difference of the norms. If you make friends with the triangle inequalities, you'll go far in real analysis. Here's a concrete example. Suppose that the absolute value of x is less than 5. That means that x is anywhere within a 5-unit radius of 0. The question is, how far away from the point 2 can x be? My diagram kind of gives away that the furthest point away from 2 is going to be the point at the left-hand endpoint of the shaded interval, which is over at -5. So the furthest possible distance is probably 7 units, but let's take a step back. What we want to do is we want to show that the distance between x and 2 is less than something. This is sometimes called controlling the distance from above. And so the forward triangle inequality is going to be our tool. It tells us that this quantity, absolute value of x minus 2, is going to be no larger than the absolute value of x plus the absolute value of -2. But we know something about the absolute value of x. Namely, we know it's less than 5. And therefore, the absolute value of x minus 2 is going to be less than or equal to 5 plus the absolute value of -2, which is equal to 7. So if we read it from the beginning to the end, we see that the distance between x and 2 has to be less than 7. The key idea here is that the triangle inequality has broken apart a distance that we didn't know anything about into a pair of distances that we did know something about. And that's where our control comes from. Here's what it looks like in a more abstract context that's typical to proofs in real analysis. Let's suppose that we know that the rationals and the irrationals are dense in one another. Why, therefore, are the irrationals dense in themselves? In other words, how do we know for any irrational number x and for any epsilon greater than 0 that there is another irrational number y within an epsilon's reach of x? What we want is to control the distance between x and y to be less than epsilon. But the theorems that we know on this slide only control the distance between rational numbers and irrational numbers. We're trying to control the distance between two irrationals. So, how can we do that? If we want the sum of the distances from x to y to be less than epsilon, what would be awesome is if we could break apart that distance into two pieces that we can control. We can do that by finding the distance from x to some rational number r, and then also the distance from r to some irrational number y, using the theorems that we're taking as a given. So we don't know the absolute value of x minus y, but we can control the absolute value of x minus r using the density of the rationals and the irrationals, and we can control the absolute value of r minus y using the density of the irrationals within the rationals. If we want the distance from x to y to be less than epsilon, it would be awesome if we could get each of those other distances that we can control to be less than 1/2 epsilon. And we can do that because those density theorems tell us that no matter how small a distance that we want, even if that distance is epsilon over 2, we can find, respectively, a rational number within an epsilon over 2 reach of x, and subsequently an irrational within an epsilon over 2 reach of r. And so what the triangle inequality will do for us is let us break apart the absolute value of x minus y, rewriting inside those absolute values by subtracting and adding r. We find out that we really have two distances that we can control, and we can break it apart by the triangle inequality into being less than or equal to the absolute value of x minus r plus the absolute value of r minus y, and each of those distances are something that our theorems let us control. The former is less than epsilon over 2, the latter is also less than epsilon over 2, and therefore the sum is less than epsilon. So now let's write the proof from the beginning to the end. We start by choosing an arbitrary irrational number x and an arbitrary distance epsilon that's greater than 0. Then, what do we want to do? We'll use the first density theorem here to guarantee the existence of a rational number r, which is an epsilon over 2 distance away from x. We'll use the second density theorem to guarantee the existence of an irrational number y within an epsilon over 2 reach of r. And then we'll use the triangle inequality to say that we can control the distance between x and y by subtracting and adding r inside the absolute value, and then breaking it apart into our two pieces, absolute value of x minus r plus absolute value of r minus y, which we can do according to the triangle inequality. And because we have control over each of those two distances, less than epsilon over 2, when I add them together, the sum is less than epsilon, which is what I wanted to prove.